To finish up the second part of chapter 6, we're going to need to discuss spline functions. We're going to go all the way from linear splines to quadratic splines, cubic splines, counting on my hand, it was just down there, you couldn't see it, cubic splines, and then touch a little bit on MATLAB implementations of a couple other spline methods that we don't have the algorithms for in the textbook. So starting with section 6.6 in the book, we're going to cover the first main part of spline interpolation. For the first time, you're not trying to find one function, one polynomial, that fits an entire set of data. We are intentionally going to split these up into chunks, where generally each function describes a particular gap between provided data points. For a few other topics, including curvature continuity, tangent continuity, other things like that, let's go to the surface for just a moment. So, like I said, if you have a whole plot of data points, A, B, and C, spline functions will be used to define one function goes from A to B, another function goes from B to C, and that would be the connections made to approximate that function. Now this is a very bad spline. We have a discontinuity here in tangency at point B. We are connected at all locations, so it's point continuous, like the edge is continuous, but the slope is not. There's a distinct slope change. So this is where the different kinds of splines come into consideration. You can have straight line splines, which of course you might expect are just called linear splines. You can have quadratic splines, which have the ability to conserve tangent continuity through points. Even though this looks like one function, it's actually is divided in between points. They are just set so that the slope is the same at the intermediate points, the middling nodes. You also have the option of using cubic splines, which honestly a cubic spline looks just about the same. Obviously these are just hand drawings, but to the plain onlooker, it looks just like a quadratic spline with tangent continuity, but the difference is this is continuous both in tangency and in curvature, the first and second derivative of the intermediate point. So for those of you who've never really dealt with curvature continuity, let's talk about what that is. In fact, I don't even really need these brackets. Let's talk about a function f of x. If that functional shape appears harsh, say it has a harsh edge. Well, that doesn't look too terribly harsh. Let's make it worse. That harsh edge. If you take the derivative of that base function, then you have more or less constant slope going up, so it'll be a positive slope, and then at this location of interest for our purposes here, the derivative suddenly shifts to a negative, constantly sloping value. The second derivative of that function, as shown, would be nothing, zero. They're flat lines. So in this case, you have a very simplistic base function, a discontinuous first derivative, and a zero second derivative. So there's no curvature anywhere. They're straight lines to begin with. If you wanted to go in and correct this, perhaps you come in and let's do the non-erase all. Let's take off this corner and put a fillet. Whether you imagine that as sandpaper or whatever, you make that curve rounded. And what you've actually done mathematically is transitioned the slope gradually between those two states. So this is what the derivative function now looks like due to your modification. And for once, we do have a part that has non-zero curvature. This would be negatively sloping, so if that was zero in the curvature plot, you'd have a region with a negative constant slope and curvature. But still, everywhere else the curvature is zero, so this shape listed up top, if it was a constant radius bend, which is the assumption I'm operating off of here, would be tangent continuous, meaning that if you touched it with your finger it would feel smooth, but it would be curvature discontinuous, as indicated here, that the second derivative jumps from some negative value to some zero value in this particular case. So the way you address this is you again round off the corners of a sharp edge, but this time you're doing it on the first derivative. So if you come in here, and if we were to erase temporarily, let me just redo that one too, and round off the corners of the first derivative, then what you're doing in the subsequent second derivative is connecting the derivative ends such that you obtain curvature continuous. It doesn't matter that it has sharp edges in the second derivative, but it is curvature continuous. What's also curious about this whole thing is that the impact on the actual function, the 0th order derivative, is minimal. The shape hardly changes. I mean, the edge just rounds off a very, very tiny amount, so there's minimal shape change required, though some is necessary, to ensure curvature continuity. And this can be very, very important for automobile reflections, can be important for optical lenses, antenna theory, other applications where the curvature of a surface is of paramount importance. So that's why splines are oftentimes used. And if they are used in these high-end curvature needs, they will be cubic or higher order splines to enable curvature continuous shapes.